This is a dramatic reading of Gamma Gamma Girl Graphs, a blog by the Stand-Up Physicist, available at science2.0.com. I got counter-snarked. At the end of my blogs, I include what I call a snarky puzzle. Now, if you can follow along with the technical parts of my blogs, then a snarky puzzle is supposed to be a playful but somewhat snide problem with a straightforward answer. One of the folks reading the post very carefully, David Halliday, actually asked a question of his own, which I will go to after setting up the context. My retitled post, Gotta Get 11 Dirac Gamma Girls plus 5 Doing an Imaginary Twist. Actually, stop. Why was it retitled? Well, I was having trouble getting the software to actually change the title at Science 2.0, and then, oops, I found out that actually it does work if you just try it again. Yeah, sometimes software is cooperative. But anyway, I was reporting on a paper that I had that was sent to me about how to use these quaternion triple products to represent the 16 Dirac gamma matrices. And in looking through the details of the calculation, David Halliday spotted this additional factor of I for 5 of the matrices. And those pesky factors of I actually means that the quaternion triple products cannot actually represent the Dirac gamma matrices. So I thought that observation was important enough to go and change the title. So let me start over. My retitled post, Gotta Get 11 Dirac Gamma Girls plus 5 Doing an Imaginary Twist, showed how to put quaternion triple products to use. The pre and post multiplying by a quaternion by one of the 4 basis vectors is what that kind of post is about. And all the triple product permutations make 16 possibilities in all. And the most useful one, I like to say, is the one that pre and post multiplies by 1. Good old unity. Why? Well, because there's nothing like staying in place. That's what most goes on in nature. You know, that planet been sitting there for over 1 billion years. Probably be there another 1 billion more. Okay. It's only when you get into relativistic quantum field theory that, well, those others really start getting on the dance floor and things get really crazy. So there are a few animations of quaternion triple products in that blog and in a video reading of it here on YouTube. Now, since David pointed out that the quaternion triple product permutations were not the Dirac gamma matrices, he pondered, you know, might there be some kind of relationship between the two, and also the Clifford algebras? And so here was his question. A snarky puzzle proposition of my own. Find an isomorphism, if possible, between the matrices of the translation table in the Gotta Get 16 Gamma Girls, and either CL22 or CL31, or both. Hint: one only needs to determine which of the matrices map to basis vectors E0 through E3, such that all of these basis vectors anti-commute with one another. And all the other matrices are given by products of these basis vectors up to a sign at least, where for CL31 the squares of all basis elements except E0 must be +1, while the square of E0 is -1. While for CL22 the squares of two basis vectors are +1 and the squares of the other two are -1. If you have the above, then the square of the product of all these basis vectors will be -1 for CL31 or +1 for CL22. Well, my short reply is simple. I don't know. But and what kind of follows you can really call numerology, because I'm basically playing with quaternion triple products. I'm making a bunch of observations, and I mean, I just don't have an overarching message to this thing. So here goes my kind of technical ramble, as it were. So David actually calculated the 16 by 16 multiplication table included actually as a comment in the thread. And I was very impressed. And David was smart. You know, he programmed a procedure to get the job done using gammas and sigmas. And I just wanted one of my own, but with quaternion triple products. And that shouldn't surprise you that I'd want to see them as quaternion triple products if you've seen any of my videos, right? And so while I was sitting through a few talks that I kind of like didn't understand at the 14th Eastern Gravity Meeting in Princeton University, I was wondering like what to do. Sit there and listen to things I don't understand? Well, that's what I was doing. But I always sit in the back row, and I could see that one of the favorite options to do is to just read your email. And other people were working on their slides. Email is email, slides are slides, what to do. Well, I was thinking about this 16 by 16 multiplication table. I said, you know, I could actually like fold a piece of paper, you know? I mean, this doesn't even have to be a fancy piece of paper. I could just fold it really precisely into like 16, you know? And then I could start to fill it in. And that's, well, basically what I did here. Oh, check that out. Oh boy. It was a long meeting, huh? Or I didn't understand much. Whichever. Okay, so I mean, I basically started filling in these 256 squares like it was a Sudoku puzzle. And actually, it really is like a Sudoku puzzle, but with a basis of 16 elements, not 9. I mean, quite literally, no element repeats in any row or any column. You know, once you've got one of those guys in that row, that's it. That row's done for that particular element. So I basically went down the column 16 times, writing one of the numbers. And then I went across 16 times, writing the same thing on the kind of outside. And then I did the calculation, and I wrote it in there, and then I looked, was it a, what I call a diagonal gamma? A diagonal gamma is 1Q1, IQI, JQJ, KQK sort of thing. Those guys I didn't color in any way. Then the 1QI, these are, I call 1 gammas because they got 1 on the left or the right, and there's 6 of those. And then there are those guys I shaded in gray. And then if it was a cross gamma, then I put in backslashes, okay? So, and then I noticed one other thing, and that is over the diagonal, if it was a negative of itself, then I try to like draw a box around it. So that took several hours, okay? And what was actually the most fun was feeling like I was doing a real hardcore physics calculation during the talks when I would have normally just like zoned out. And I even was able to summarize the statistics of this one. It's kind of neat. So David's investigations used graph theory to look at different little parts of the structure. And I'd also done some graph theory with quaternions. There's a talk here about quaternion multiplication for third graders, which has graph theory actually done with clay and pipe cleaners. Okay, so the next step should actually kind of give you a sense of what I'm like as a scientist. I mean, I decided to do the completely labeled graph for the multiplication table, and I would not stop until everything was done. And once done, I would then look for simpler patterns. And so here is the final result. Yes. This was done with a program called Inkscape, which is an open source program. The SVG file is available for download if you're interested. I mean, it's kind of dense, huh? It's every bit of as dense with information as the multiplication table. And the file has, I think, more than 30 layers in it. So that makes it possible to kind of focus in on smaller subjects. So let's think about the other extreme, and that would be the 16 vertices. Now, at the dead center is the identity triple product 1Q1. Surrounding it are the three diagonal gammas, always dressed formally in black. That would be IQI, JQJ, and KQK. And the blue ring of 6, those are the 1 gammas, because blue ribbons are given for first place. So that's 1QI, 1QJ, 1QK, KQI, KQJ, KQ1, JQ1, IQ1. There we go. All right. And the outer ring are the red cross gammas. So that's IQK, IQJ, JQK, KQJ, JQI, KQI. That should cover it. Now, if any of these 16 are squared, then the result is either going to be a positive number or a negative sort of thing. And the positive ones live on the diagonals and the diagonal gammas, I'm calling them, and the cross gammas. And they've got those solid lines connecting them because it's the same to go in as to go out. Now the negative ones are actually all the 1 gammas. And I actually had to do a correction on this one on my original post, because David Halliday pointed out that in an earlier version I had some solid lines, but the correct version really needs the dashed lines to indicate that the label changes depending on what the starting vertex happens to be. So going out from the origin requires the positive sign, while coming in requires the negative one. In fact, just like happens with imaginary numbers. Imaginary numbers are just like that. 1 times an imaginary number brings you out to an imaginary number, but if you're out at an imaginary number, you need to multiply it by minus the imaginary number to get back to 1. So, a few technical points. I have represented these as unidirectional graphs because the label is the same no matter which way the product is formed. So an I prime, Q, I prime, I, that actually is the same as if you flip those I's around, you know? But David pointed out that there's really still are two directions. And I'm kind of confused as to what situations would there be where it would actually make a difference. I mean, as long as you write down all the labels and all the vertices, well, then it should be okay. But problems do come up if you don't write out all those parts. Okay. So I also included these identity bubbles, these little loops there with the 1Q1s in them. And that was actually unfortunate in a way, because without them, I could have called the positive identity guy K1, 9 or S9. That actually stands for the complete graph that connects one central dot to 9 on the edge. That's K1, 9, making it a star, literally S9. The negative identity graph would have been K1, 6 or S6. But I feel that the loops are necessary because I was using the identity matrix already, you know, and if you're using that, you got to show it wherever it comes into play. And I mean, I realize that it's common practice in graph theory not to include them. The loops can make a simple graph no longer simple. Being complete, though, is more important to me than being simple. The big messy graph, in fact, would be called K16, everything and its brother, actually, if I just didn't include those little identity loops. That makes it a different, gives it a different kind of properties. So the graph for the diagonals, when I drew it out here, that's actually shocked me, okay, when I included the identities with the diagonals. Okay, so this is not going to shock many people, but I actually wrote a blog about it already, the Quaternions for a third grader. This is the graph of the Klein group. I did not expect it to show up in this exercise. I started to use this graph in a quest to characterize a symmetric metric changes caused by gravity. But then I caught an error in that kind of analysis, pointed out again by this David Halliday fellow, because he pointed out that while the graph looks similar to the Klein group, well, actually without any labels in there, it is the same darn thing. Once you start putting in the labels, there definitely is a difference between this graph and the Klein 4 group. The reason is that this one has 6 distinct labels for the edges. You see the positive ones on the inside and the minus ones on the outside, whereas the Klein 4 group, that only has 3 distinct labels. And I'm going to be, doing research on the differences in the coming weeks and months. So the next level out are the 1 gammas, and here are the directional graphs for this shared label. This graph is known as K3, 3, which has a name actually, the utility or Thomson graph. And I just want to add another observation, and that is it took me quite a while to see K3, 3. That stands for actually the complete graph of 2 kind of subsets that totally check each other out. Think of it that way. In fact, I had to ask a question out at math.stackexchange.com. Someone pointed out that if I just traded places with two of the vertices across the center, that I would end up with the standard way that people draw K3, 3. There still might be something going on with the labels. You know, I'm always now suspicious of graphs that don't include all that information. But this graph is toroidal, meaning that it fits nicely on a torus. And David actually was able to spot that property with his own explorations. So there are edges where the sign flips one way versus the other. I use this dashed line and a double-headed arrow to kind of mark these. And so here are the anti-symmetric 1 gamma multiplication graph. And you can actually see two separate triangles, and in graph theory nomenclature they call that K3. The K actually is German for complete, all right? And what he and then David, you know, got on my case again, and he said, you know, you should combine this 1 gamma anti-symmetric stuff with the relevant identities, and when you do put these two together, well, the result looks like a quaternion, amazingly enough. The graph of a quaternion, because everybody's got this, you know, go in with a negative sign, come out with a positive sign from unity, and we're all connected, and we form this tetrad, and yeah, that's basically the graph of a quaternion. Now, if you combine these K3s with the two K3s with the utility graph, or K3, 3, then you actually get K6. Now, if I had actually studied graph theory, I might have actually known that already. So the cross gammas also have a utility graph. Okay, here's another correction. Am I a professional graph theorist? No. Okay. And well, I mean, while that graph does have 6 vertices and 9 edges, like K3, 3, I don't see how to separate that into two distinct sets of triplets. In fact, about all I can see to do there is it really looks like I can make 3 pairs, you know, but that's not the same thing. So I'm really not sure what to call it. Maybe there isn't a name. Who knows? The anti-symmetric gamma graph multiplication graph actually connects all 6. And this graph is called C6. Some introductory graph theory book probably explains why combining all this stuff together does make K6. So we can form other complete graphs between, say, the diagonals and the 1 gammas, and this gets classified as K36. And there's another K36 between the diagonals and the cross gammas. Now, I don't know if these two are technically different. That would have to be an issue addressed by someone more skilled in the arts of graph theory. And finally, there is a K66 for when the 1 gammas and the cross gammas just try and do everything they possibly can. So I'm going to stop with the numberology exercise there. I plan on repeating this work with clay and pipe cleaners, and that might just take some time. Not. All right, so here is my snarky puzzle mystery. Usually I know the answer. This time I don't. So that will make writing the answer kind of harder for me, but I doubt you care. So I went out on a limb to embrace something I called California numbers. Now, being from the East Coast, I had trouble doing that, you know. I mean, I have a friend who lives out there who who's into like barefoot running, and he's wearing these shoes that have individual places for each toe. Now, in this blog, generating the California numbers multiplication graph using only quaternions was really kind of cool. Now, I just want to see if numerically you can show that the two are the same, California numbers or quaternion triple products. Now, if this can be done, I'll be able to stay on the East Coast with my division algebra of quaternions. All right. Thank you very much.